Chapter 12 is going to be about sound, and since it's the last chapter, it's the sound will be of cheering. Contents of Chapter 12, we're going to talk about what sound is and some of its characteristics. It's going to be a lot of relating back to Chapter 11 for some of this stuff. Talk about how sound is going to have intensity and how the ear responds to that, just very briefly. Sources of sound, we'll be looking at musical instruments, vibrating strings and air columns, so flutes and violins, if you will. Talk about having more than one sound at once and how sounds can interfere with each other. Doppler effect, how sound can be shifted by an object or having a source that's moving or observed that's moving. Lastly, talk about shock waves, the sonic boom, and just some applications of sound, sonar, ultrasounds, medical imaging. So let's talk about some characteristics of sound, remembering that sound is a wave, and more specifically it's going to be a transverse wave, so the particles are moving back and forth and the wave is traveling in the same direction as the particles. Sound can travel through any type of matter, however it cannot travel in a vacuum because there are no particles to vibrate back and forth. So you see Star Wars and stuff like that and you hear the laser sounds. Really not true, because there are no particles in space, so sound cannot travel through a vacuum. The speed of sound is different in different materials. Generally slower in gases and faster in liquids and faster still in solids, and that's related to essentially how well objects can transfer the sound from particle to particle, kind of how elastic that is. Typical value we're going to see and use is air, 343 meters per second. That's kind of an average speed. It's going to depend on temperature, pressure, and a few other things, but in general we're going to be using this value right here. And you can see how as we go from gas to liquid to solid, the speed of sound drastically increases. Other characteristics of sound, we might talk about the loudness. That's really related to the intensity, or the power divided by the area of a sound wave. Musicians will often talk about pitch. In physics, we're going to be talking about the frequency, which is related to the pitch of a musical instrument. The audible range, this is kind of the audible range that we as humans can hear of frequencies, and actually it's really quite large, going from 20 hertz to 20,000 hertz. However, as you tend to age, you tend to not hear higher frequencies, so it might decrease to say 15,000 hertz. And I swear now that I've had a daughter, it's probably because she screams at above those frequencies and I just don't want to hear it. Ultrasound, you may have heard of ultrasound technology. That's going to be, we'll talk about that briefly at the end of the chapter, and that's going to be using frequencies of sound much larger than 20,000 hertz. And lastly, infrasound, that's going to be frequencies that are below 20,000 hertz. You typically, this would be sound that you can perhaps feel but not hear with your ear, at least unaided ear, and you'll typically see things like animals doing this. Some whales might make sounds in that region. Let's talk now about the intensity of sound, and we're going to introduce a concept of a decibel. We've already introduced sound as having an intensity, which is going to be the power divided by the area, where if you remember, the power is simply the energy per unit time, so the intensity is going to be energy per unit time per unit area, and we'll talk about that typically with having a unit of watts per square meter. And it's actually quite amazing. Our ear can detect sounds with intensity as low as 10 to the minus 12th and as high as 1 watt per meter squared. So we can hear a very large dynamic range of sound. It's actually quite an amazing phenomenon. However, when we talk about intensity, or sound level, or volume if you will almost, we're not necessarily talking about intensity. We're talking more now about a sound level, which is going to be a level at which we can hear above our threshold of hearing. So you can see sound level here. It's in this interesting unit of decibel right there, named after Alexander Graham Bell. If we're ever talking about intensity or we're talking about power, then you want to use the version over here where it has watts per meter squared. If we're talking about sound level, then we want to talk about it in terms of decibels, not in terms of watts per square meter. So this table right here shows the intensity for various sounds, both in terms of this sound level in decibels as well as the intensity. You can see that the sound level in decibels is baselined to be 0 at the threshold of hearing, which does have some power associated with it, and goes all the way up to 140 decibels, a jet plane at 30 meters. One thing to keep in mind is, suppose you're talking, or suppose you're at a noisy restaurant and you're reading some 10 to the minus fifth watts per square meter. You're also registering 70 decibels. If you double that, you double 70 decibels, now we're not talking about 10 to the minus fifth, we're talking about 10 squared in terms of intensity. So you can see that simply doubling the sound level is going to increase the intensity not by a factor of 2, but by a factor of 7, 10 to the 7th. So we just have to be very careful whether we're talking about sound level or intensity. So the loudness of a sound is much more so related to the sound level in decibels, which, as you can see on the last slide, doubling the sound level gave us a 10 to the 7th increase in intensity. The reason for that is because there's a logarithm hidden behind the conversion between sound level to intensity. Equation 12.1 here gives us a relationship between our sound level in decibels, which is that symbol beta right there, and the intensity right here. That's going to be the I guy, relative to some reference intensity, which we typically take to be the threshold of hearing. So recalling from the last slide, we had the sound level at the threshold of hearing was 0 decibels. The reason for that is because we had 10 log of I naught over I naught, and the log of 1 is equal to 0. The unit being decibels. One thing to note is actually decibels is a unitless measure of an object. It's really just to remind us that we're talking about a sound level, much like the radian was to remind us we're talking about an angle. We take a logarithm of an object and we're going to have no units associated with it. If you're looking at this expression right here and you're not 100% up to snuff with your rules of logs, I highly suggest you take a look at these guys, because I'm going to be using them. I'll be giving you this equation and expecting you to rearrange it as well. Just one refresher, suppose you had something like 10 log of I divided by I naught. That's going to be equal to 10 multiplied by the quantity log of I minus log of I naught. And you also might want to look up the rule of multiplication for logs. Taking a look at an increase in sound level, looking at specifically example 12.4, if we were listening to a jet engine and all of a sudden it fires up its second engine, we want to make sure that we add the intensities. We don't want to add the sound levels. If we add the intensities, essentially double the intensity, example 12.4 shows that actually we're just increasing the sound level by 3 decibels by doubling the intensity. So in terms of sound level, it's quite small, just 3 decibels, even though we've doubled the intensity. One thing to keep in mind is remember that intensity is equal to power divided by area, and typically the area is going to be the area of a spherical wave, as I discussed in chapter 11. So it's going to be power divided by 4 pi r squared. So the intensity here is going to die off like 1 divided by r squared, and as you back further and further away from things, the intensity is going to die off not like r, but like r squared. So if you double your distance, your intensity has gone down by 4, not by 2. In enclosed spaces, it is very, very, very complicated and well beyond the scope of this course, but we have to worry about reflections and frequencies getting absorbed and all sorts of crazy things that you don't want to worry about. So what happens for our hearing? We're going to obviously hear from our ears. We're going to have sound waves coming into our ear. So here I'm drawing the wavefronts, or all of the crests coming into an ear, and that's going to hit a membrane. It's got a fancy scientific name, but we call that our eardrum. And our eardrum is going to start to vibrate back and forth. Those vibrations go through the hammer, stirrup, and anvil, 3 little bones in our ear here. And that's going to have our cochlea right here. That's going to put vibrations into that. This thing is full of fluid as well as essentially little hair follicles, and these hair follicles are going to vibrate back and forth, and we're going to turn this mechanical wave into electrical energy for our auditory nerve. Really, the ear is broken up into 3 main pieces: the outer ear, which allows the sound to travel down the canal to the eardrum, which is going to be a vibrating membrane. The middle ear simply is just going to transfer the vibrations to the inner ear, to the cochlea, and then this cochlea is going to transform that vibrational energy into electrical energy, which is then sent to the brain. So the ear is going to respond differently to different frequencies that are instant upon it. In general, we're sensitive to 20 hertz to the 20 kilohertz range. I mentioned that before. I'll mention it again because we use it in a homework problem. And if we look at lines of constant perceived loudness, it's going to be labeled FONs, but really you can think of this as constant perceived decibel range. It's kind of interesting to say, let me look at this point right here. I'm perceiving a sound level of 60 decibels, and however I'm looking at something that is going to be on the 40 decibel line here, and that's at a frequency of 100 hertz. That's going to be the same, that's going to have the same perceived loudness, the same decibel level, as something that is 60 hertz and at 1000 hertz, and so on and so forth. I can see that just simply because I'm looking at different frequencies, I'm going to perceive different sound levels. Now that we've talked about some of the nuances of sound, let's talk about how we can produce sound. Let's look specifically at musical instruments. Something that all musical instruments have in common is they are going to resonate. So musical instruments are going to be resonators. So we've actually talked about that a little bit in the last chapter. We're going to expand on it in this chapter here. What can be resonating? We can have strings that are resonating, vibrating back and forth, string instruments, membranes, drums, vibrating metal or wood, so reed instruments, and lastly we can actually cause air columns to resonate. If you've ever blown into a soda bottle, or if you're talking about musical instruments, we're talking about flutes, and we can essentially create this resonance by plucking, striking, bowing, or blowing on whichever instrument we're trying to make resonate. And then these vibrations, these sound waves, are going to be transmitted through the air using longitudinal waves, and then to our ears, as I discussed on the last slide. So first let's talk about vibrating strings, which actually we've already talked about in chapter 11 when we talked about these things called standing waves. So you might want to go back and refresh yourself on those guys. Here we've pinned down the guitar at the two endpoints, so we're going to have two nodes for the fundamental frequency there and there, and at the middle we're going to have the anti-node. Now we can relate the length of the guitar to the wavelength as we did in chapter 11. It's going to be half of the wavelength. You kind of see this is 1/2 of the wavelength, and now I've drawn one full wavelength for the guitar. So we could also say that the wavelength is going to be twice the length of the guitar. And we know how wavelength is related to frequency. The frequency is going to be the velocity of the wave on a standing wave divided by the wavelength. So the fundamental, I'm putting a 1 right there, is going to have a frequency of velocity divided by twice the length of the guitar. So to change the fundamental frequency, we can change the length of the guitar simply by fingering it right here. Essentially what we're doing is we're shortening the length, and so we're raising the frequency. We also know that the velocity of the wave is going to be related to the tension right there divided by the mass of the string. So we can also change the velocity of the wave by tuning the guitar, by tightening the strings. If we tighten the string, we're going to increase the velocity of the wave, we're going to increase the frequency, and we're going to have guitar strings that have different masses or different densities. Remember, this little mu guy right there is the mass divided by the length. So if we increase the mass of the string, we're going to lower the velocity, and we're going to lower the frequency. And last but not least, we can write the secondary frequencies as we did in the last chapter, simply as being the n multiplied by the fundamental frequency, where n is going to be 1, 2, 3, 4, and so on and so forth. For wind instruments, we're going to now have air columns that are going to have standing waves inside of them, and we're going to have the same thing. We're going to have nodes and we're going to have anti-nodes, only now rather than having a string that's going to have nodes and anti-nodes in terms of the string, now we're going to be talking about nodes and anti-nodes in terms of pressure inside of this air column. It turns out that we can have two types of vibrating air columns. We can have a tube that's open at both ends or a tube that's closed at one end, both of which are going to be able to generate standing waves. Let's first talk about a tube that's open at both ends, which most wind instruments actually are. It's going to have, we can look at this in terms of pressure nodes or displacement nodes and antinodes at the ends. I find it personally easier to think about it in terms of the displacement of air. However, you can also think about it in terms of pressure. If we look at the displacement of air and we say at the ends of this tube, the air molecules are pretty much free to leave the tube and come into the tube without anything impeding them. And so the displacement of air is going to be quite large at the two endpoints. So here and right here over here. Now in the middle, it's much less free and much less able to vibrate back and forth. So what we're going to do is we're going to have antinodes in terms of displacement at the two endpoints, and we're going to have nodes in terms of the displacement in the middle. What we can do now is we can relate this wavelength right here to the length of the tube, and you can see, knowing what we already know from the string instruments, that the length of the tube is simply going to be 1/2 of the wavelength. And much like we did for the stringed instruments, we can write down the fundamental frequency. For the second harmonic, it's going to be very similar. We must have the displacement of air be antinodes at the two endpoints, and at the middle now, we're going to have an antinode, and these points right here, we're going to have nodes. This is the second harmonic, much like it was for the string instruments that we talked about for chapter 11. We can relate this wavelength to the length of the instruments. You can see that this is one complete wavelength here. So the second harmonic is going to have the wavelength being equal to the length of the tube. Also relate that to frequency. And we do the third harmonic more or less in the same way. So we can see that we can write our frequency as being the for any given harmonic as n multiplied by the first harmonic right there, and we can calculate the first harmonic knowing the speed of sound and the length of the tube. For a tube that's closed at one end, it's a little bit more complicated and a little bit more interesting too. What I'm looking at in terms of the displacement of air is the air at the tube now cannot leave the tube as it could in the open tube sense, so I must have a displacement node at this end right here, the closed end. I must always have a node there, and I must always have an antinode right here because the air can freely leave the column. So the first way we can draw the displacement of air in terms of a wavelength is going to have the antinode there and then the node here. If you look at that, the length is going to be related to the wavelength as simply 1/4. So if I wanted to complete my wavelength, that's going to be 1/2 of a wavelength, and so on and so forth. So now I've drawn one complete wavelength. You can see how this right here, that length is going to be 1/4 of the wavelength, and we can write our frequency as such. This is going to be the first harmonic, or the fundamental frequency. Now for the next possible harmonic, we must have the node at this end and the antinode right there. The only way that we can draw that is to have the node here come all the way up through an antinode, back down through a node, and then have an antinode at this end right there. If you take a look at that, that's actually going to be 3/4 of the wavelength. And if we want to compare that to the frequency, that's going to actually be 3 times the original fundamental frequency right here. So we're only going to have odd harmonics for a tube that's closed at one end. There is no possible way for the second, fourth, sixth harmonic to be able to meet this criterion of having a node at the closed end and an antinode at the open end. For the fifth harmonic, it's going to be very similar. We can relate the length to the wavelength and the frequency to the harmonic. So for any given frequency, we can write the frequency to be n multiplied by the fundamental frequency, but now we're going to say n is only going to be odd. It's going to be 1, 3, 5, 7, and so on and so forth for a tube that's closed at one end. You might be asking yourself, so, why do instruments sound differently? And the key is it's going to be in the overtones that are present. So if I pluck a string, I'm definitely going to have the first fundamental frequency, but I may also have some of the second overtone, and I may even have some of the third overtone. So I can have more than one frequency coming out of my stringed instrument. For other instruments, the relative amount of the overtones is going to be different. So this plot right here shows the relative amplitude versus the frequency for a clarinet, a piano, and a violin. And you can see for a clarinet, this relative amplitude is going to say there's a lot of this frequency, not so much of that frequency, and we're going to also have all of these overtones coming out of the instrument. for a piano, it's going to have a lot of that frequency, and actually a whole lot of overtones going out to 2500 hertz. A violin's going to have fewer overtones. So all three of these instruments can be playing the same note, but they're going to have different amounts of relative amplitude in the overtones, and that's what's really making them sound different.